Hi everyone, and welcome to this fourth seminar on our series of talks of the alumni of the University of Queensland alumni in name of the SFP student chapter from the University of Queensland. I would like to thank you for attending this seminar, and I would like to introduce Dr. Mateo Gutierrez. He is one of the most recent alumni from our fire safety engineering research group, and he's currently the technical development manager at CLTP Tasmania, a startup company located in Wynyard. There, he oversees the manufacturing of engineered timber based on a sustainable approach, and his research interests primarily are focused on the novel construction and building materials, mainly in systems using timber and bamboo. So with no further ado, I'd like to introduce to you Dr. Mateo Gutierrez. It's really nice to have you join us today. So the floor is yours, Mateo.
Thanks, Julian, and good afternoon, everyone. I'm very pleased to be here this afternoon. It's a pleasure to give a talk in the SFP UQ chapter. Not very far ago, I was sitting in the other side, like looking at other alumni and other practitioners in our field. And it's a great opportunity, and I'm very happy to be here today. I'm going to start sharing my screen, and we can start with the presentation. Can you see the screen, Julian?
Yeah, that's perfect. You're good to go.
Great. All right, so the title of my presentation is From Burning Bamboo to the First Commercial Plantation Hardwood CLT in the World. And as you can infer from the title, I will mainly divide my presentation into two main parts. The first one will be focused on the latest outcomes of my PhD, which was focused on the fire performance of bamboo structures. And in the second part of the presentation, I will give you a glimpse of the work that I'm currently doing at CLTP Tasmania, where we are developing a sustainable approach for processing plantation hardwood into engineered wood products, mainly glulam and CLT. So let's get started. This journey basically started in 2010 when I started my master's in structural engineering at Columbia. I decided that I didn't want to study like conventional materials like concrete and steel. I wanted to focus on alternative solution, and I wanted to look for like more sustainable materials. So at that point, I started studying bamboo, and back in 2015, I said, well, I want to do my PhD, and I really wanted to do it in bamboo after have done my research and after practice in designing with bamboo houses. So for many of you, bamboo is not a familiar construction material. Bamboo is not very used in Australia, but bamboo is a very, very common material around the world. More than 1 billion people live in bamboo houses. Bamboo is mainly used in low-rise construction, like residential dwellings, like in community centers, or like, for example, in this sports hall that is located in Thailand. But bamboo can be also used in like multi-story houses, like 3 or 4 story houses. You see a couple of examples here. This is a house in China. On the left-hand side, you see a house in China, and on the right-hand side, you see a hotel in Bali, where you see the application of round bamboo. But we not only use round bamboo as a construction material, similar to timber, bamboo has been also evolved into engineered products. So the most common engineered bamboo product is laminated bamboo, which is basically made of bamboo strips. So you have as you see here in the picture, let me just put set up the pointer. So you have round bamboo that is split, and then those strips that you get out of the bamboo column, you plant them, and then you apply glue, you press them together, and then obviously you create larger cross sections. This is a laminated bamboo beam made out of Philostachys pubescens, which is the most common bamboo species in China and the most common bamboo species used for the manufacturing of engineered bamboo products. With engineered bamboo, obviously you can go or move from irregular circular cross sections like the ones you have in round bamboo to regular and standardized cross section, rectangular cross sections that obviously can be larger, and because they are larger, they can withstand higher loads. And obviously, as in any other engineered products, you reduce the variation in the mechanical properties, and obviously you can have more reliable and stronger load-bearing elements. There are applications for laminated bamboo, more similar to the ones that you see in mass timber construction or in light timber framing. And of course, when I started my PhD and I moved to UQ, our fire safety engineering group is focused on the fire performance of materials and the use of fire or the understanding of the fire performance in the built environment. So we decided to perform or conduct a research on the fire performance of bamboo. And of course, bamboo, as any other combustion materials, face the same issues when it's subjected to a fire. It burns and it loses integrity, and it can lead to the collapse of bamboo structures made out of bamboo. So you see here on the left-hand side, this is a house in Mexico. They were welding some steel connections, and obviously that led to a fire. Here you see another structure in Bali. This was one of the main engineered bamboo manufacturers in Bali. You can see here this concrete column. This is what it was left after the fire. So again, round bamboo, because of its geometry and because of its mechanical properties, can lose very quickly its strength, and obviously can lead to structural collapse. This is another sad example. This is the biggest engineered bamboo supplier in Europe. So you see here, this is the factory of Mosso International in the Netherlands. And as you can see here in the picture below, the adjacent building where they used to store all the engineered bamboo products obviously got burned and collapsed after burnout. So we found that there was a very little understanding on how bamboo behave during a fire. Obviously, because more than a billion people live in bamboo houses, bamboo is being already used. There is already a hazard if we don't know how to design bamboo to withstand a fire. And there is a potential for using bamboo in mid-rise construction or even in high-rise construction. Future applications for laminated bamboo can be used in mid-rise constructions and high-rise constructions where fire could be a significant problem. So we believe that we needed a methodology to facilitate performance-based design solutions with bamboo. And we also wanted to have the same confidence that we have in other conventional materials. So to be able to do all of that, we require a better understanding of the structural fire performance of bamboo. So the methodology that we propose can be divided in three main stages. The first part was focused on understanding the mechanical properties at elevator temperature. And the properties that we choose were the compressive strength, the tensile strength, obviously the modulus of elasticity in both type of loads. And we look at the failure modes, and we try to make some constitutive stress strain constitutive models at elevator temperature. With the information in the material level, then we move to a bigger scale, and then we wanted to predict and understand the performance of load-bearing elements. And we mainly choose columns, short columns, and bamboo beams. I will show the results today about the beams. And finally, we wanted to create some analytical models that were able to help us to predict the performance of those members. Like if we had the mechanical properties, and if we understood the variation in the mechanical properties, if we created those constitutive models, and if we have the experimental test results at a bigger scale, then we wanted to see if the models could predict that behavior. So we start testing laminated bamboo in compression. We did the first test in round bamboo, but we quickly realized that round bamboo lose strength very quickly. So during a fire condition, we definitely wanted to have like bigger cross sections, and that's when we decided to put more attention into the engineered bamboo products. So we basically expose laminated bamboo elements or specimens in an environmental chamber where we could carefully control the temperature. We established correlations between surface temperature and internal temperature of our specimens, and we were able to understand the reduction in the compressive strength. We also measured the reduction in the modulus of elasticity, and we tried to recreate the stress strain behavior of bamboo under compression. We kind of repeated the same process with the tensile strength. We conducted several tests at different temperatures, from ambient temperature around 20-25 degrees to up to 200-250 degrees, right? Again, we measure the reduction in the modulus of elasticity, and we measure the reduction in the tensile strength. We perform some DMA, dynamic mechanical analysis, in small scale samples, and we compare the results of the dynamic analysis, of the dynamic mechanical analysis, against the results at the bench scale. So what you can see here is the reduction, the normalized modulus of elasticity against temperature. And these are the results of the DMA, and this is the reduction in the MOE at bench scale, which told us that the results match pretty well both medium and small scale. With all that information, we created some reduction factors for bamboo at elevator temperature. Reduction factors for the compressive strength, which is the black line here. Reduction factor for the tensile strength, which is this line, and then obviously the reduction in the modulus of elasticity. So what you can see here is that, for example, at 100 degrees, bamboo loses almost 70% of the compressive strength. And that's a significant reduction. Like if we think that the temperature during a fire is, you know, at 1200 degrees Celsius, this is telling us that we very quickly start losing the capacity of load-bearing bamboo members. So the reduction in tension is not that critical. And obviously a reduction in the modulus of elasticity again is not that critical. But after 150 degrees, where we have, where we observe the onset of pyrolysis, the reduction is way more considerable. So, and then after 250, the material is completely charred, and the strength and stiffness of bamboo can be neglected. So we describe that reduction with these equations, and based on that reduction and in our stress strain models, then we propose stress strain models for compression and a stress strain model for tension. Tension is a little bit easier because bamboo is pretty much elastic in tension, and it has a brittle failure. Compression is a little bit more complicated because you see a lot of plasticity. And again, you can use very complicated models, but we ended up going for a simplistic approach and see if that simplistic approach could give us an accurate result, right? So we proposed to use a perfect elastoplastic model that obviously was changing in function of temperature. So again, we describe the performance with bamboo with different equations. Those equations were function of temperature, and then with these constitutive stress strain models, then we move to the next stage, which was the analysis of bending specimens exposed to fire. So in order to test those elements, we again decided to go for the simplest scenario, which is a simply supported beam loaded in 4-point bending, right? So obviously you have the maximum bending moment in the central third of the beam, and we expose that part to fire, right? But conducting fire experiments is not an easy task. We obviously couldn't carry out those experiments at the instructor's lab because of the release of smoke and because of the elevated temperatures during the test. Obviously, we were also creating some risk for the equipment. So we decided our own testing setup, and that was like one of the biggest tasks of my PhD, designing this setup. So basically what we did is we turned this upside down. So instead of applying the loads downwards, we applied the loads upwards, right? So supports are here, you have your specimen here, and then we have an actuator. The actuator was using a transfer beam, and obviously these were our loading points. And in order to apply the fire, we have our extraction hood here. We have radiant panels. The radial panels were providing a constant heat flux. And obviously we start burning the central third of the beam, where we have the maximum bending moments. So before applying the test, you can see the setup here. This is a video of a test at ambient temperature, so without any fire until basically reaching the fire. So you can see the actuator going up, you see the loading points. We use DIC, digital image correlation system, to be able to track the displacements and the strain, but we also use contact sensors. So we use string pots, and we also use strain gauges. But again, this is a test at ambient temperature, the same test that you usually do when you are applying the load downwards. But again, we wanted to do it here because we needed to apply the external heat flux. So what you see here is a radiant panel. These gypsum boards were protecting the other part of the beam that we didn't want to expose to a fire. And again, in the second part, so from the results of this test at ambient temperature. We basically obtain our failure loads in bending under that particular configuration. And obviously we understood the force deflection curves. With that information, then we define 3 different stress levels. We apply 54% of the failure load, 40% of the failure load, and 27% of the failure load. So remember that from the previous test, we defined our failure load, which was around 15 kilonewton. So 8 kilonewton, 6 kilonewton, and 4 kilonewton allow us to test 54, 40, and 27% of the failure load. And obviously, we expose those beams to the same external heat flux, which was 60 kilowatts per square meter. And what we basically did is that we apply the load until we reach this stress level. And at that point, we apply our constant heat flux. We measure the distance between the radiant panels and the beam before starting the test. And that's what define the heat flux. We run several calibration with a heat flux meter, and we were quite confident that we were exposing our beam to a constant heat. So here you will see a typical test. So you see that the actuator is going up. We are applying the load until we reach the desired stress level. So imagine that this is, let's say, 6 kilonewton, 6 kilonewton force, right? Once we reach that desired stress level, we turn on the radiant panels. We wait until the radiant panels reach like a steady state condition, so the heat flux was uniform. And after that point, we ignited the sample. And obviously, once the sample ignites and once you start burning the specimen, the specimen starts getting more stress until, and obviously start having more and more deformation until it finally reached the failure. We also use electronic pressure valve that was controlling the pressure in the actuator and was giving us feedback. So in order to maintain the desired stress level, we were always changing the pressure in the actuator to keep a constant pressure. And obviously, because we have a constant pressure and we had like a temperature penetration, and obviously we were burning the sample, finally the sample ended up reaching the failure at some point. One of the more innovative approaches in this test setup was the use of the DIC in a fire application. So what you will see here, this is a zoom in of this area here, right? Of the middle third of the beam. So again, you see here, this is the actuator, this is the load cell, this is our transfer beam, this is the central third of the beam. And again, here you have displacement against time, right? So basically, we start loading the beam until we reach the desired stress level. And then at that point, we start the fire exposure. And you see that the beam start increasing the displacement until it finally reached the failure. The DIC not only allows us to capture the deflections, but it also allows us to capture the stress and the strain in the beam. So what you will see here is, again, strain against time. You will have tensions here, compressions here, and you will see the strain in 3 points. At the bottom of the beam, like in the furthermost fiber, bottom fiber in compression in this case, because again, remember that we are loading upwards. So you're gonna have the opposite that you normally have in a conventional test setup, compression at the bottom and tension at the top, right? You start loading the beam, you have compressions here, tensions here, right? Tension, compression, and the neutral axis where the strain is pretty much zero. And then you start burning the beam. Once you start burning the beam, you have more strain, right? Because you start increasing the stresses, right? Until you finally reach the failure. What is really, what it was really nice and really cool about this system is that you can see the fire propagations and you can kind of anticipate where the failure is gonna occur, right? Because you can see which parts of the beams are subjected to higher strain and of course higher stresses. In order to measure the temperature profiles and the in-depth temperatures in our specimens, we perform some control tests with some in-depth thermocouples. We didn't want to affect our specimens during the fire structural experiments. So we performed some tests with the same situations that we had in our structural test, right? To measure the temperature distribution in the beam. So again, we have set up different thermocouples. We measure the temperature profiles for different times. You have temperature against time. Before starting the test, you have pretty much the whole beam at ambient temperature. After 10 minutes, you start seeing some charring, and obviously you start having higher temperatures closer to the exposed surface, right? And obviously temperatures start increasing in the whole cross section after a certain period of time. So that was pretty much the setup and the results of the experimental test. Then we move into the numerical model. So it was a very simple numerical model. You can use the same kind of analysis that you do at ambient temperature. We decided to use a section analysis. So basically we had our beam. We divided that beam in different slices. We know the properties of each slice, and obviously if we apply fundamental equations, we can predict the bending moment capacity. The good stuff here is that you can use stress strain models, so you can predict the plastic zone. And as we know in timber and in bamboo, when we have tensile failures, we usually reach the yielding in compression, and obviously we can have better prediction for the bending capacity. The difference here is that once we expose this beam to a fire, the properties of our cross section are not constant anymore, right? Because we are going to have a temperature distribution. So each fiber in our cross is going to have a different mechanical property, because this is what we found in the first part of the PhD, that the mechanical properties were changing in function of that internal temperature. So what we proposed basically was use the same section analysis, but then changing the mechanical properties of each fiber. So you can divide that cross section in as many layers as you want. You will assign like those stress strain models for each of the fibers, and obviously you apply again structural equations, like equilibrium equations to obtain the bending, the capacity. But you not only predict the capacity, you can also predict the stress strain profiles. And because the continuous lines, you will see that they are the experimental results. These are the results for the 4 kilonewton test. And the red dashed line is the prediction of our model. So the model, because we assume that after 250, you will lose all the strength, that's pretty much what is showing the progression of the char depth, right? And you see that the results of our model match pretty well the experimental results of the test. We also compare the experimental results in the bending capacity, or what many people understand as the fire resistance, right? So you see that for 8 kilonewton, the time to failure was around 8 minutes. For 6 kilonewton, the time to failure was around 16.5 minutes. And for 4 kilonewton, the time to failure was around 22 minutes. With our model, we kind of predicted that reduction in the load bearing capacity. And we observed that the variation between the experimental results and the numerical model was around 11% difference. So we also propose a model to calculate the deflection. So you see, this is the deflection against time of exposure, right? So here are the results for 8 kilonewton. Here you have the results for 6 kilonewton, and here for 4 kilonewton, which again, in the where the material behaves quite elastic, it's quite good. But after we are reaching the, we are very close to the failure, then we have more difference in our model and our experimental results. But again, the concept was again very simple. You had a part of your beam that was changing properties because of the effect of temperature. We managed to predict the reduction in the stiffness, and obviously with the reduction in the stiffness, we were able to calculate the deflections. When you look at the results here, this is the temperature profile of your beam. So you have temperature against depth. That's the depth of the beam at the back. And you can see that the char front, if we use the conventional approach that we currently use in timber, which is assuming that the 300 degrees isotherm is what defines the char depth, right? You see that the failure occur way above that char front, right? So, and this is because of the influence of the heated depth, right? We observe that bamboo has like a significant reduction at very low temperatures, like below, you still have a significant reduction below 100 degrees. This is for tension. Remember that this is the side that is exposed. So yes, well, what I'm trying to say here is that the conventional approach of the reduced cross-section method could be not very accurate to describe the performance of bamboo because of the thermal properties and because of the reduction in the mechanical properties. So again, we also compare the results of the reduced cross-section method. So if we use the conventional approach of the reduced cross-section method, assuming that the charring rate for bamboo will be 0.7 millimeters per minute, you will see that this is the reduction. So basically at 8 kilonewton, we should have obtained a failure around 25 minutes, but at the end, we did it at 8 minutes. And again, we also try to apply the reduced cross-section method, but instead of using a conventional charring rate, we use the results of our experimental test for 60 kilowatts per square meter. And even though we had very accurate charring rates, which in some, if I remember well, they were like up to 1.3 millimeters per minute, you still over predicting the fire resistance of bamboo. So obviously, of course, our model is way closer to reality, and this allows us to get like way better results. So in conclusion, this study, developed like novel experimental setups for testing load-bearing members or charring load-bearing members under fire exposure. and the use of DIC was very beneficial to understand the performance of those materials. We obtained a reduction in the compressive strain, tensile strain, and modulus of elasticity for bamboo at elevator temperature, and we managed to create equations for these properties as a function of temperature. We propose different constitutive stress strain models to predict the performance of bamboo at elevator temperature. And we obtain stress strain profiles, bending capacity, and deflections as a combination of heat transfer models and thermomechanical models through the use of constitutive stress strain models. So again, for the heat transfer models, we just use experimental results measuring the in-depth temperatures, but as many of you know, some other PhD students are working on numerical heat transfer models, which in the future will help us to predict those in-depth temperatures. So yes, we use a quite simplistic analysis for the developing of those stress strain models. You can use more complex analyses like 3 linear models or even polynomial models, but this approach was enough to get very close to the results. In the second part, I will talk about this product development at CLTP, and I'm going to do this very quickly because we're running out of time. But I think, as many of you are already, or I was expecting to have a lot of students, there is the transition from doing the PhD into going to industry was quite interesting for me, and it's something that many of you will face very soon. For those who are not familiar with CLT production, CLT is an engineered wood product. What we are doing at CLTP Tasmania is using a timber resource that has never been used for the production of engineered wood products. The species that we use is Eucalyptus nitens. It's a timber species that it's been normally used for paper production, for the production of paper pulp or wood chips. So that was quite interesting for me and for the industry itself. So again, you have logs, you cut those logs, you dry them, you do some grading before you finger join them. Then you plant those lamellas, apply glue, make for glue laminated timber, you put all the lamellas in the same direction. If you're doing cross laminated timber, you cross layers next to each other and to be able to make panels. And then once you have your panels, you cut those panels normally in CNCs, you package those panels, and then you bring it to the construction site. So here you have your beautiful eucalyptus plantations. Then you take them to the factory, dry them, put it into the CLT vacuum press or mechanical press if you're using mechanical press, and then obviously cut the panels and then send it to the construction site. So that was the state of the factory in September of 2019, before when I was finishing my PhD. And this is the factory, or that was the factory in July 2020, almost a year ago. So you see that there was like a very quick transition, a very quick evolution of this company. And obviously I was involved in all of that as a technical development manager right after finishing my PhD. So some of the main areas of work was to develop a kiln drying program for this species, creating a quality assurance framework to manufacture GLT and CLT, installing and commissioning a lot of new equipment, as you saw from the previous picture. And again, that was only the manufacturing plant. We have another facility where we dry the timber and do the grading. A lot of training has been involved, training our staff and training for myself as well, and for and for everyone, you know, supervising and coordinating the operation of this facility. We have done a lot of testing to understand the properties of those products. I created an in-house laboratory for factory production control. And obviously, we have worked obtaining different type of certifications to position the product in the market. And of course, what it could be very interesting for some of you, we have also done some work in the fire performance of these products. So kiln drying was like a massive challenge for us. You see here timber in the kilns, and obviously some of the changes that the timber goes through in this process. That's been a massive amount of work dedicated to that area. Finger jointing of lamellas to be able to put it in the vacuum press and produce CLT. Again, we created a quality assurance framework. We had to control many different variables during the production of these products. Like we need to control glue rates, we need to control pressure, we need to control temperature, we need to be aware of the climate conditions when we produce these products. Many things we have to control. And obviously we need to comply with some existing standards, Australian standard for the production of finger jointed lamellas and glue laminated timber. There is no Australian standard for the production of CLT. So we use ISO standards and European standards as a reference. A lot of training is being involved, and obviously as a technical manager, I've been involved in a lot of that, creating training material and performing training. We have done a lot of tests. We have done it at the feedstock level, right? So characterizing the material that we are going to be using in those products. Of course, all type of structural tests, from bending, compression, tension, shear, parallel shear, perpendicular shear, to testing the system itself, like testing the engineered products. So in this case, a lot of testing in the CLT, as you can see here, but we have done a lot of testing in GLT as well. So bending, rolling shear, compression, and pure rolling shear, as you see in this picture. That's the lab where we are doing factory production control. We have to test daily our finger jointed lamellas. We need to test our feedstock to control the material that we put in our products. We do a lot of testing in our glue lines, right, to control the bond quality of these products. We look at the delamination, we look at the thickness of the glue line. Like when you expose glue line to UV lights, you can measure the thickness. And again, we work with the certifiers that control our process and that certify that we are complying with these manufacturing standards. So yeah, different processes like EWPA, but we are also, have like Australian made certification that we produce all our material here in Australia, and FSC and PFC to prove that we are using a sustainable approach and sustainable plantations. And of course, some work has been done in fire as well. We are currently defining our fire testing program. But as many of you know, like the fire resistance of CLT depends on many different things, like the geometry, the thickness of the lamellas, the properties of our feedstock, the loss of or the reduction in the strength and the stiffness, as I explained before in bamboo, the use of different insulation materials, the use of joints, connections. So it is a complex program, and I'm working on that. So at the end, we're very happy with the results. After this year, we have already produced some very beautiful products. This is some CLT panels from our first commercial project. You see the finish of and the appearance of the panel, which made us feel very proud because, again, this is a timber species that no one have ever thought that we could use in this type of applications. And with all the work that we have done in the last year, we are making this option a reality. So in conclusion, yes, your technical skills are very important. And after finishing a PhD, they are very important because they give you a lot of confidence. But as a technical development manager, I have also seen that soft skills are equally important. You need to have a lot of communication to be able to transfer your knowledge and to be able to transfer your ideas. You need to have a lot of creativity. There is a lot of problem solving in our roles as a technical experts. So you should have a lot of empathy. You need to have adaptability because industry moves pretty quickly. After doing a PhD and being focused on the same research topic for many years, well, more than 3 years, change into going to industry, it could be challenging. And of course, you're always in a continuous learning process. Having a PhD or just finishing a PhD just means that you are able to learn quicker, or you are able to find answers, like in the right place, but you're always going to be learning. So that's pretty much my takeaways, and I hope you have enjoyed this presentation, and I'm happy to take questions if we still have some time. Thank you.
Thank you, Mateo, for this amazing talk and guiding us through your research and your personal and professional experience in this new stage. We still have 30 minutes for questions, so some of them have already been asked in the chat. So I'll read them for you. So there are plenty of them related to your research. So I think we will start with that.
Mm-hmm.
One of them, I think you actually already answered, but just to be sure, from Greg Baker, he asks if you did measure the actual charring rate of your samples during the tests.
Yes, I measure charring rates, or I measure the 300 or the movement of the 300 isotherm. But I think one of the findings of my research is that I will think that the 300 isotherm is not the right temperature to define char depth in bamboo, because what I observed from my mechanical test at elevator temperatures is that after 250 degrees, the strength and the stiffness can be completely neglected. So yes, we measure in-depth temperatures. With the in-depth temperatures, you are able to measure charring rates, but the main focus of my research was actually not using charring rates, but using reduction in the mechanical strength and mechanical properties to predict the fire resistance. So I can answer the other two questions there, which is related to creep. Under constant load at ambient, yes, bamboo suffers creep, but I didn't do any creep test. Bamboos, as timber, is affected by creep, but all the tests that I did were short duration tests. What's the critical heat incident heat flux of bamboo? I didn't do any work on critical heat flux, but you can refer to Dr. Angela Solarte. She conducted a lot of experiments in bamboo flammability, and she obtained critical heat flux for bamboo. If I'm not wrong, critical heat flux of laminated bamboo is around 14 to 15 kilowatts per square meter. Yep.
Okay, thank you for your answers. As Mateo was mentioning, we also host a talk with Dr. Angela Solarte. If you are interested in the topic, you are free to go to our YouTube channel where we are going to have the recording for this talk and the past talks. And anyway, you are also encouraged to contact the presenters if you have any other questions. Yeah. So following up with the questions, we have some other related to the thermal strength. So you're being asked if you consider the thermal strength for or the bamboo expansion in the models you developed.
No, I didn't consider any expansion, thermal expansion. What I observe in the literature is that timber, what they usually do in timber is that they neglect the thermal expansion because you have also shrinkage due to loss of moisture content. So the way that they assume is that the what you usually have as expansion can be contrasted by the shrinkage due to loss of moisture content. So in timber and in this case bamboo, this phenomenon can be neglected, or I think that's the reason because I did it. Can you do it? Yes, you probably will be free to do it, but that they will definitely complicate the analysis. Yep.
Okay. And following on the methodology for your research, Greg Baker asks, why did you select 60 kilowatts per square meter as the incident heat flux?
We selected that heat flux because we had a lot of information about that type of, or that incident heat flux. Another PhD student, Ian Pope, which is about to finish his PhD as well, he did a lot of tests under that constant heat flux. So we thought that understanding the behavior, thanks to Ian's results, that was going to facilitate the analysis of my beams. So that was why we decided to choose 60. 60 is also like a high, relatively high heat flux as well. So of course we were trying to represent like a real fire, and 60 kilowatts gave us confidence to say that that was kind of a similar type of heat flux that you can have in a real fire. Again, there are testing restraints, you know, like the type of heat flux that we can achieve in the fire laboratory. So yeah, there were a lot of discussions about choosing a certain heat flux, and yes, 60 was the one that we decided because of the reasons that I just explained.
Okay, thank you for your answer. Yeah, I agree with you. That can be one of the most challenging things working with fire, how you try to represent the real life conditions, but how you're limited in the lab for technical or safety reasons as well. So following with the questions, you were also asked when you applied the reduced cross-section method, if you consider a zero strength layer, and if yes, how much was it?
That's really very interesting question, because yes, when we applied the reduced cross-section method, again, there wasn't any research done in bamboo, or there wasn't any values proposed for bamboo. What you conventionally see in timber is the zero strength layer is 7 millimeters. And 7.5 millimeters, and if I'm not wrong, Strand Standard recommends 7. We use that, but we knew that that value doesn't represent the zero strength layer in bamboo or the heated depth in bamboo, because bamboo has a higher thermal conductivity than timber. So what you usually see is that the heated depth is bigger in bamboo than in timber, and obviously that matches the results that we got in our experimental test.
All right. So thank you for your answer. Also, more regarding towards the conditions of your experiments, what were the lamella dimensions for the bamboo sections in your specimens?
Laminated bamboo, it will definitely depend on the type of bamboo or the bamboo species that you are using. Because of the very thin cross section, I actually have a piece of bamboo here. So remember that you are trying to have rectangular cross sections out of, circular cross section. So bamboos that we use for laminated bamboo are normally called woody bamboos, and they have diameter of around 120 to 160 mil, and the thickness of the wall is around 10 mil, 10 to 15 mil. So those strips are usually 4 to 5 mil by 20 mil, right? So that's usually the size of the strips, because then you also need to have like a minimum length. The length of those strips are usually 2.4 meters or 3 meters. And obviously bamboo is a taper material as well. So yeah, you're kind of restrained by the geometry of bamboo.
Okay. Yeah, depends on a lot of factors, as you were explaining. And finally, there is one question related to the density of the timber and the trees, and I guess this one is related more with the ones you're using in your current job, since that question was asked during that section.
Eucalyptus nitens is a plantation hardwood. As a hardwood, it usually has like higher densities than softwoods. The density of this particular species and the timber that we are currently using is around 570, 580 kilograms per cubic meter in average. But we have variations from 480 up to 700, 750 kilograms per cubic meter. The bamboo, the trees that we are using are from 16-year-old up to 26-year-old trees.
Okay, okay. Thank you for your answers. So I'd like to ask our attendees if you have any more questions for Mateo. In the meantime, I would like to thank you for your amazing presentation and for sharing all of this knowledge and your personal experience as well. It seems we have another question. Yeah, I don't know if you'd like to read it or me read it for you, as you wish.
Yes, I can see it here. Moisture content in my samples, raw bamboo had like a moisture content around like 9%, and the moisture content in laminated bamboo was around 7%. Yep.
All right. Yeah. Okay. So in this case, As we don't have any more questions, I would like to conclude this seminar here, thanking our presenter, Dr. Mateo Gutierrez, and also all of our attendees for joining us today. I would like to remind you this talk and previous talks are going to be in our UQ SFP chapter YouTube channel. So if you are interested in Mateo's talk or Mateo's topic or any of our previous presentations, feel free to look for us in YouTube and you're gonna find the information. You're going to be sent the link as well in case you want to join further of our talks or in the future. So yeah, I would like to thank you and remind you of that. It seems we have another, yeah. Thank you, Greg, and thank you everyone for joining us in name of the UQSFP chapter. I would like to wish you all a great weekend and thank you again.
Thanks a lot. Thanks for having me, and thank you everyone for your questions and for attending the presentation. It was a pleasure.
Nice. Have a good one.
Bye. Cheers.